2.5 million times the volume of Earth is hidden inside a single world in our own backyard. Yet for most of human history, we have completely misunderstood what that world actually is. Every textbook you ever opened, every classroom model, every children's book illustration got Jupiter fundamentally wrong. They called it a gas giant. They told you it was a big ball of hydrogen and helium with maybe a rocky pebble at the center, wrapped in pretty clouds. That picture is now dead. Jupiter is not a gas planet at all. It is a liquid planet, and the overwhelming majority of its 143,000-kilometer diameter is an ocean of liquid hydrogen capped by a 40,000-kilometer deep sea of liquid metallic hydrogen that behaves like a molten metal. The colorful clouds we admire are only the top 50 kilometers, a paper-thin frosting on a cake made of impossible physics. The numbers themselves are violent. Jupiter contains 317.8 times the mass of Earth. If you took every other planet in the solar system, Mercury through Neptune, added them together, then doubled that total, you still would not reach Jupiter's mass. Its equatorial diameter stretches 142,984 kilometers. Earth could roll through that distance 11.5 times before it touched the far side. Stack Earth on Earth like cannonballs, and you would need 1,321 of them to equal Jupiter's volume. Or, to use the comparison that finally makes the human brain stall, if Earth were reduced to the size of a standard grape, 22 millimeters, Jupiter would be a perfectly round beach ball 2.46 meters across, weighing as much as 95 fully grown African elephants. That is not a planet. That is a failed star that simply didn't collect enough material to ignite. With only 13% more mass, it would have become a red dwarf, and our night sky would have 2 suns. Instead, it sits at 79 Jupiter masses, the exact sweet spot where gravity crushes matter into states we cannot reproduce in any laboratory on Earth for more than a few microseconds. We used to think the interior looked like a layered cake, thin gas envelope, thick gas envelope, small rocky core. That model survived from the 1970s until roughly 2016. Then NASA's Juno spacecraft arrived and spent 8 years screaming through Periyov passes only 4,000 kilometers above the cloud tops, tasting the gravity field with a precision of 1 part in a billion. The data came back so strange that the mission team had to invent new mathematics just to describe what they were seeing. The old cake was wrong. There are no clean layers. There is no sharp boundary between anything. Instead, Jupiter is a single, continuous gradient of hydrogen that changes its personality as pressure climbs. Gas to supercritical fluid, to liquid, to exotic quantum liquid, to metallic conducting fluid, to partially dissolved core. Instead, it sits at 79 Jupiter masses, the exact sweet spot where gravity crushes matter into states we cannot reproduce in any laboratory on Earth for more than a few microseconds. We used to think the interior looked like a layered cake, thin gas envelope, thick gas envelope, small rocky core. That model survived from the 1970s until roughly 2016. Then NASA's Juno spacecraft arrived and spent 8 years screaming through Periyov passes only 4,000 kilometers above the cloud tops, tasting the gravity field with a precision of 1 part in a billion. The data came back so strange that the mission team had to invent new mathematics just to describe what they were seeing. The old cake was wrong. There are no clean layers. There is no sharp boundary between anything. Instead, Jupiter is a single, continuous gradient of hydrogen that changes its personality as pressure climbs. Gas to supercritical fluid, to liquid, to exotic quantum liquid, to metallic conducting fluid, to partially dissolved core. The entire planet is one unbroken fluid body undergoing the slowest, most violent phase transitions in the solar system. The visible clouds are not even the beginning of the story, they are the end. They are the cold, low-pressure exosphere of a world whose true surface lies 1,000 kilometers underneath them, where hydrogen is forced into a liquid state, not by cold, but by raw compression. 20,000 kilometers lower still, at pressures of 45 million atmospheres and temperatures exceeding 10,000 degrees Celsius, that same hydrogen is squeezed so hard that its electrons detach and roam freely, turning the liquid into a shining metal that conducts electricity better than copper at room temperature. This metallic ocean is 40,000 kilometers deep and generates a magnetic field 20,000 times stronger than Earth's, a field so powerful it would instantly destroy any unshielded electronics in Jupiter orbit, and flings radiation belts that bathe the moon Io in 400,000 volts per meter. And at the very center, where older models drew a neat, Earth-sized ball of rock and iron, Juno found something far weirder. A fuzzy, dilute core that occupies nearly half the planet's radius. Heavy elements are not neatly settled. They are mixed upward into the metallic hydrogen in a swirling, semi-dissolved soup that may extend 60,000 kilometers outward from the center. The traditional sharp core mantle boundary simply does not exist. Jupiter ate something enormous in its youth, probably a super-Earth 10 to 20 times our planet's mass, and the collision was so violent that it never allowed the heavy elements to settle again. The scar of that impact is still there, 4.5 billion years later, written in the gravity anomalies Juno mapped in excruciating detail. We are not looking at a planet in the way we understand Mars or Venus. We are looking at a star that lost the ignition lottery and instead became the most extreme laboratory of high-pressure physics in the accessible universe. Every single assumption we carried into the year 2000 has been demolished. The only thing that survived is the name gas giant, and even that is now a cruel misnomer. Jupiter is not gas. Jupiter is an ocean planet, whose ocean is deeper than the distance from Earth to the Moon, capped by a metallic conductor that powers aurorae bright enough to be seen from the next star system, wrapped in a 50-kilometer thick blanket of clouds that we mistook for the whole show. This is not the Jupiter your teachers described. This is the real one, and we have only just begun to meet it. Let us now force the human mind to actually feel what these numbers mean, because Jupiter does not merely look big in telescope images. It is big in a way that breaks every instinct we evolved on a small rocky world. Start with mass. Jupiter weighs 1.898 times 10 to the 27th kilograms. That single object contains 317.8 Earth masses. Take every planet, moon, asteroid, comet, and speck of dust orbiting the Sun beyond Jupiter, and their combined mass is still only 0.38 Jupiter masses. Jupiter is 71% of everything in the solar system that is not the Sun itself. The Sun is 99.86% of the total system mass. Jupiter is most of the remaining 0.14%. Everything else we have ever stood on, flown past, or photographed is a rounding error. Now, volume. Jupiter's equatorial diameter is 142,984 kilometers. Earth's is 12,742 kilometers. Divide them, 11.21. So Jupiter is 11.21 Earth diameters wide, but volume scales with the cube of diameter, so 11.21 cubed equals 1,408. You can fit 1,408 Earths inside Jupiter without any of them touching. The often quoted 1,300 Earths is slightly out of date. The precise current figure using Juno's refined radius is 1,408. For a comparison that actually hurts, if Earth were a standard NBA basketball diameter 23.8 centimeters, Jupiter would be a sphere 2.67 meters across, roughly the height of a tall basketball hoop. That sphere would weigh 952 kilograms, almost 1 metric ton of pure planetary material hanging in mid-air in front of you. If you tried to dribble it, the ground would disappear long before the ball did. Density tells a different story. Despite being 318 times more massive than Earth, Jupiter's average density is only 1.326 grams per cubic centimeter, less than a quarter of Earth's 5.51 grams per cubic centimeter. That sounds gentle until you realize it is still 24% denser than water. If you found a bathtub large enough, Jupiter would sink slowly and majestically while displacing an amount of water equal to 1,408 Earth oceans. Rotation is where the violence becomes obvious. Jupiter spins once every 9 hours, 55 minutes, 30 seconds, the fastest of any major planet. That means a point on its equator is moving at 45,360 kilometers per hour, 12 times faster than Earth's equatorial speed. The centrifugal force is so extreme that the planet is visibly squashed. Equatorial diameter 142,984 kilometers. Polar diameter 133,708 kilometers, a difference of 9,276 kilometers. That bulge is larger than the entire diameter of Mars. The oblateness is 1 to 15.3, meaning if you looked at Jupiter edge-on from the pole, it would look 6.5% wider than it is tall, like a pumpkin someone sat on. Gravity at the cloud tops, 1 bar level, is 24.79 meters per second squared, 2.53 times Earth gravity. Drop a hammer there and it accelerates downward almost 2.5 times faster than on Earth. But because the planet is spinning so furiously, the effective gravity you would feel standing on the clouds is only 2.14 g, because centrifugal force is throwing you outward at 0.39 g. If Jupiter spun only a little faster, the equator would be in orbital velocity and material would simply fly off into space. Escape velocity from the cloud tops is 59.5 kilometers per second, almost 5 times Earth's 11.2 kilometers per second. Fire a rocket straight up at 60 kilometers per second and it will never come back. That is why Jupiter has held on to every atom it ever collected for 4.6 billion years, including lightweight hydrogen and helium that leak away from smaller worlds. Internal heat output is another shock. Jupiter radiates 1.6 times more energy than it receives from the Sun. Total power output, 8.3 times 10 to the 17th watts. Equivalent to 200 trillion nuclear power plants running continuously. That heat is leftover from formation plus slow gravitational contraction, the Kelvin-Helmholtz mechanism. Every second, Jupiter shrinks by about 2 centimeters, converting gravitational potential energy into heat that drives the wild weather we see. The Great Red Spot alone is 16,350 kilometers long and 12,000 kilometers wide, 2024 measurement. Earth's diameter fits inside it 1.3 times with room to spare. The storm is currently shrinking at roughly 900 kilometers per year, but even at its present size, it could swallow 3 Earths side by side and still have space between them. Jupiter's magnetic field reaches 4.2 Gauss at the cloud tops, but the magnetosphere extends 1 to 3 million kilometers sunward and trails out past Saturn's orbit in the most extreme cases. The trapped radiation belts deliver a dose of 500 sieverts per day at the orbit of Europa, enough to kill an unshielded human in minutes. Every single one of these numbers is measured, not guessed. Juno's 8 years of gravity mapping, Doppler tracking from Earth, microwave radiometry, and magnetometer passes have nailed them down to parts per million. We are not dealing with estimates anymore. We are dealing with a world whose vital statistics are now known more precisely than those of any planet except Earth itself. And yet, with all that mass, all that heat, all that spin and magnetism, Jupiter still failed to become a star by the narrowest cosmic margin. Add just 80 more Jupiter masses, roughly the content of the Orion Nebula's richest star-forming region, and nuclear fusion ignites. Instead, it stopped at exactly the size where gravity can do the most exotic things to matter without ever crossing the line into stellar fire. Jupiter is the largest possible planet that can exist without becoming something else entirely. That is the scale we are actually dealing with. Not big, not huge, but the absolute maximum expression of planetary existence before physics says, no, now you are a star. Everything about it is tuned to the breaking point of what a ball of hydrogen and helium is allowed to be. In July 1994, the solar system put on the most violent fireworks show in recorded history, and it did it on purpose just to teach us how little we actually knew about Jupiter. Comet D/1993. F2 Shoemaker-Levy 9 had been quietly orbiting the Sun for decades, maybe centuries, when Jupiter's gravity reached out in 1992 and ripped it apart like wet tissue paper. The comet crossed the Roche limit, the invisible line where tidal forces exceed self-gravity, and shattered into at least 21 major fragments stretching across 1.2 million kilometers of space. Astronomers on Earth watched in stunned silence as the broken pieces lined up like pearls on a string, each one doomed to dive straight into Jupiter's atmosphere 2 years later, in July 1995. The largest fragment, named G, was roughly 2 to 2.5 kilometers across, possibly as much as 4 kilometers if later density revisions hold. It was not a fluffy snowball. It was a dense rubble pile of ice, dust, silicates, and organic compounds moving at 60.57 kilometers per second relative to Jupiter, 216,000 kilometers per hour. When it hit, the entry velocity plus Jupiter's own gravity accelerated it to a final impact speed of approximately 61 kilometers per second. The first piece, fragment A, struck at 2013 UTC on July 16, 1995. Over the next 6 days, 21 separate fragments slammed into the planet's southern hemisphere between 44 degrees and 48 degrees south latitude. Each impact occurred on the far side, hidden from Earth for about 10 minutes until Jupiter's rapid rotation brought the fresh wound into view. The largest explosion came from fragment G on July 18th at 7:33 UTC. It released kinetic energy equivalent to 6 million megatons of TNT, roughly 600 times the entire global nuclear arsenal at Cold War peak, or 300 million Hiroshima-sized bombs detonating in the same spot within a fraction of a second. The fireball rose 3,000 kilometers above the cloud tops, higher than the diameter of Earth. Temperatures inside the plume spiked to 24,000 Kelvin for a few seconds, hotter than the surface of the sun. The shockwave raced around the planet at over 1,000 meters per second and was detected as a seismic wave in the atmosphere itself. When Hubble, Galileo, and every major observatory finally saw the scars, they were not small dark spots, they were black continents. The biggest impact site from Fragment G was 12,000 kilometers across, almost the size of Earth itself. The debris clouds were darker than any natural feature ever seen on Jupiter, absorbing 99% of visible light because they were loaded with sulfur compounds, carbon, and complex organics dredged up from depths we had never sampled before. The plumes ejected material at over 15 kilometers per second, fast enough that some of it reached escape velocity and was flung permanently out of the Jovian system. For weeks afterward, the stratosphere was laced with new molecules never before detected: hydrogen cyanide, carbon monosulfide, carbon disulfide, and metallic compounds like iron, magnesium, and silicon in vapor form. The impacts injected at least 2 times 10 to the 11th kilograms of cometary material into the upper atmosphere, equivalent to a layer 1 millimeter thick spread over the entire planet. Infrared telescopes measured temperature spikes of several thousand degrees persisting for days. The scars glowed in methane and ammonia absorption bands for months. The great dark spot from Fragment G was still visible in amateur telescopes a full year later. This was not a surface event. The fragments exploded at altitudes where the pressure is only 1 to 5 bar, roughly the same as Earth's upper troposphere, yet the energy was so immense that it punched clear through the visible cloud deck and excavated material from depths of several hundred kilometers, possibly as deep as the water cloud layer at 5 to 10 bar. For the first time in history, we were handed a free core sample from the interior of a gas giant, blasted into space and laid out for spectroscopic analysis. Astronomers expected to see mostly ammonia and hydrogen compounds. Instead, they found sulfur, heavy metals, and an astonishing amount of water, far more than any pre-impact model predicted. The comet itself was only 50 to 60% water ice, yet the plumes contained water signatures orders of magnitude stronger than could be explained by the impactor alone. The only possible conclusion: Jupiter's atmosphere below the visible clouds is far richer in water than anyone had dared suggest. The old dry formation models, which claimed Jupiter formed beyond the snowline but somehow stayed bone dry, collapsed overnight. The impacts also revealed Jupiter's atmosphere rings like a bell. Global oscillations were detected for weeks afterward, giant gravity waves circling the planet at speeds up to 200 meters per second, visible as concentric ripples in the cloud tops. These were not weather patterns. They were actual acoustic modes of the entire planetary body, the same kind of global resonances seismologists use to study Earth's deep interior. From those waves, scientists derived the first crude constraints on the deep density profile long before Juno ever arrived. Shoemaker-Levy 9 did not just scar Jupiter, it humiliated every textbook model we had. It proved that violent energetic events can dredge up material from depths we thought were forever inaccessible. It forced us to accept that Jupiter is chemically stratified in ways we never imagined, and that its interior is far more complex, far wetter, and far more dynamic than the neat layered cartoons we had been drawing for decades. The comet was a messenger that arrived at exactly the right moment. Galileo was already en route, carrying an atmospheric entry probe timed to arrive just 5 months later. The stage was set, the planet had been cracked open, and now a spacecraft was coming to fly through the smoke and taste what had been hidden for 4.5 billion years. On December 7th, 1995, 5 months after the last black scar of Shoemaker-Levy 9 had finally faded, a 339-kilogram copper-colored bullet named Galileo's atmospheric entry probe punched into Jupiter's sky at 47.8 kilometers per second, 169,488 kilometers per hour, the fastest human-made object had ever entered any atmosphere. It hit the atmosphere at 5.8 degrees north latitude, deliberately placed in a region far from the impact scars, so the data would represent normal Jupiter, not a wounded one. At entry interface, defined as 450 kilometers above the 1 bar level, the deceleration slammed the probe with 230 g, 230 times Earth gravity. The heat shield, made of carbon phenolic, reached 15,500 degrees Celsius on the front face and lost 79 kilograms of its original 152 kilograms of mass to ablation in the first 2 minutes. It was the most violent controlled entry ever attempted by humanity, and it worked perfectly. 61 seconds after the peak heating, at 157 kilometers altitude and Mach 48, the drogue parachute popped, followed 3 seconds later by the main 2.5-meter parachute. The probe slowed, stabilized, and began its 75-minute descent through the darkening sky of Jupiter. The first surprise came almost immediately. The probe entered one of the pale zones, a region we thought was calm and cloud-free. Instead, it found almost no clouds at all for the first 50 kilometers. The expected thick ammonia cirrus deck at 0.5 bar was missing. The probe fell through nearly clear air until it reached the deeper water cloud layer, where it finally encountered dense clouds and powerful downdrafts of 150 to 180 meters per second, 540 to 650 kilometers per hour, winds blowing downward, the strongest vertical motions ever measured on any planet. Then came the measurement that rewrote every single textbook written before 1996. The Galileo probe carried a helium abundance detector built to 1% precision. Everyone expected the helium mass fraction to be roughly 0.238, the same as the Sun, because Jupiter was supposed to be primordial gas that never differentiated. Instead, the probe measured 0.135 plus or minus 0.003 by mass, 18% helium by number, far lower than the Sun's 24%. That single number proved beyond doubt that helium has been settling toward the core for billions of years, raining out of the upper layers in microscopic droplets, exactly the way lead separates from lighter elements in Earth's core. Jupiter is not a frozen snapshot of the solar nebula. It is an evolving, differentiating world. Next came water. Pre-mission models predicted the probe would see water abundance rising steadily with depth as it descended past the predicted cloud base. Instead, it saw almost none, less than 0.03 times solar abundance at the 12 bar level. Then suddenly, at 19 to 21 bar, just before the radio signal died, the mass spectrometer spiked to nearly 0.5 times solar, and the data cut off. The probe had finally punched into a deep, hot, water-rich layer, but it was already too deep, too hot, and running out of power. The official explanation is that the probe entered an unusually dry hotspot, an infrared hot region where giant downdrafts evaporate clouds and concentrate clear, dry air. These hotspots cover only about 1% of Jupiter's surface, but are so extreme that they mimic desert conditions on a gas giant. The probe just had the cosmic misfortune of landing in the one place on the planet where water is locally depleted. Yet even that misfortune was a revelation. Jupiter's atmosphere is far more patchy, far more Earth-like in its variability than anyone had imagined. Temperature rose steadily, minus 108 degrees Celsius at 0.4 bar, plus 22 degrees Celsius at 4 bar, warmer than Earth's tropics, plus 127 degrees Celsius at 12 bar, and plus 152 degrees Celsius at the last reading at 23 bar. Pressure climbed to 23.5 bar before the signal was lost, equivalent to being 235 meters underwater on Earth. The probe was still 500 to 600 kilometers above the level where liquid hydrogen begins, yet it was already in an environment hotter and denser than the bottom of the Mariana Trench. Wind speeds told another story. At the entry altitude, winds were only 80 meters per second. By 5 bar, they reached 150 meters per second, and they kept increasing with depth, exactly opposite to what happens on Earth, where winds die out below the cloud layer. On Jupiter, the deeper you go, the faster it blows, peaking at over 180 meters per second in the probe's descent path. These are not surface winds. These are jet streams driven by heat rising from thousands of kilometers deeper, powered by the planet's internal furnace. The final transmission came at 57 minutes, 36 seconds after entry, from a depth of 156 kilometers below the 1 bar level and a pressure of 23.5 bar. The probe was still descending at 15 meters per second when the link failed, probably because the antenna could no longer point toward the orbiter through the increasingly dense plasma sheath. It continued falling for another hour or more, eventually vaporizing somewhere near the 100 to 200 bar level, still less than 1% of the way to the center. But in those 75 minutes, Galileo's probe delivered the first direct chemical assay of a gas giant atmosphere. It measured ammonia, hydrogen sulfide, methane, water vapor, germane, arsine, phosphine, molecules that only exist because material is being dredged up from depths where temperatures exceed 1000 degrees Celsius. It proved that Jupiter's upper atmosphere is depleted in helium and neon, that it is patchy in water, that its winds grow stronger with depth, and that the old uniform, well-mixed model was hopelessly naive. Most importantly, it confirmed what Shoemaker-Levy 9 had hinted at. Jupiter is wet, far wetter than anyone believed possible for a planet that formed at 5.2 astronomical units. The probe just happened to fall through the one dry throat on the planet, but the spike at the very end told us the truth. Deep water clouds exist, and they are rich. Juno would spend the next quarter century proving it. Galileo's little probe died screaming in fire and pressure, but before it did, it whispered the most dangerous sentence in planetary science. Everything you think you know about Jupiter is wrong. On July 4th, 2016, at 8:53 p.m. Pacific Time, a 3.9-meter-wide spacecraft traveling 58 kilometers per second fired its main engine for 35 minutes and 13 seconds and let Jupiter catch it forever. Juno did not just arrive, it surrendered to the monster. And for the next 8 years, it would scream past the cloud tops at only 4,100 kilometers altitude, closer than any moon, every 53 days, then fall outward to 8 million kilometers before being dragged back again. Each period was a near-death experience, radiation doses of 20,000 rads per pass, magnetic forces strong enough to twist titanium, and gravity gradients so violent that the spacecraft's own spin changed measurably. Juno was built to survive only 37 orbits. It is still flying as of 2024 on its 61st science pass, and it has completely demolished the last remnants of the 20th century picture of Jupiter. The revolution began with the very first gravity pass in August 2016. Juno carries two instruments that turned out to be lethal weapons against old theories. A microwave radiometer, MWR, that can see 600 kilometers beneath the clouds in 6 wavelengths from 1.3 centimeters to 50 centimeters. And an exquisitely sensitive gravity science experiment using the spacecraft's X-band and K-band radio systems to map the planet's gravitational field to 1 part in a billion. The gravity data arrived first, and it was immediately obviously wrong. In every pre-Juno model, Jupiter's interior was symmetric north-south. The gravity field should have been almost perfectly even, with tiny perturbations from rotation. Instead, Juno measured massive asymmetries. The northern hemisphere is gravitationally heavier than the southern by hundreds of kilometers worth of mass. The odd harmonics, J3, J5, J7, J9, were not microgauss level noise. They were screaming at thousands of times the predicted amplitude. Something enormous was moving inside Jupiter, and it was not evenly distributed. By Perigove 8 in September 2017, the team had enough data to publish the first conclusion that made planetary scientists choke on their coffee. Jupiter has no sharp core mantle boundary. The old Earth-sized dense core does not exist. Instead, heavy elements are partially dissolved and mixed into the metallic hydrogen envelope in a diffuse central region that extends out to nearly 50 to 60% of the planet's radius. The core is not a ball. It is a fuzzy, slushy, semi-dissolved zone of rock, ice and metal swirling inside liquid metallic hydrogen like sugar half stirred into coffee. The microwave radiometer confirmed it from a completely different direction. Deep atmospheric sounding revealed that ammonia is not well mixed globally. Instead, it is concentrated into a gigantic equatorial belt that extends from roughly 30 degrees north to 30 degrees south and plunges at least 350 kilometers deep, possibly deeper. Outside this belt, ammonia is heavily depleted all the way to the equator to pole boundary. This is not a thin weather layer. This is a planet-scale structure, a hidden ammonia-rich ocean beneath the visible clouds that behaves like a separate dynamical region. The belt is so enriched that the total mass of excess ammonia is equivalent to several Earth oceans worth of NH3 dissolved in hydrogen. Then came water. By combining microwave brightness temperatures with gravity constraints and updated equations of state for hydrogen-helium mixtures under pressure, the Juno team announced in 2018 and refined in 2020 to 2023 that Jupiter's global water abundance is 1 to 4 times solar, possibly as high as 6 times solar in the deep interior. That means between 8 and 25 Earth oceans worth of water locked inside the planet, most of it dissolved in the deep hydrogen envelope under pressures, where water becomes a supercritical fluid or even ionic conductor. The old dry Jupiter hypothesis is dead and buried. Jupiter is wetter than any terrestrial planet except Earth itself. Juno also measured the magnetic field at close range and discovered it is a nightmare. The dynamo is not a smooth dipole like Earth's. It is lumpy, chaotic, and dominated by a powerful northern hemispheric flux bundle nicknamed the Great Blue Spot, a region of intense magnetic field near the equator that is shrinking and drifting westward at 4 centimeters per second. The field strength at the dynamo surface, around 0.9 Jupiter radii, reaches 20 to 25 Gauss, 4 to 8 times stronger than previous models allowed. The field is generated not in a thin shell, but in a thick zone of metallic hydrogen starting at roughly 0.8 to 0.85 Rj and extending inward with contributions from helium rain, compositional gradients, and possibly even magnetic diffusion from the dilute core. By 2021, the combination of gravity, microwave, and magnetic data forced a completely new class of interior models called dilute core or fuzzy core models. In these models, the central 15 to 25 Earth masses of heavy elements are not compacted into a dense ball, but are smeared out over 40,000 to 60,000 kilometers by a giant impact early in Jupiter's history. The impactor, probably a 10 to 20 m protoplanet, struck head-on or nearly head-on, dumping enough energy to erode and mix the original compact core into the surrounding metallic hydrogen. The heavy elements are still slowly trying to settle, but convective currents keep them stirred. The process will continue for billions of years more, gradually forming a proper core long after the Sun has died. Juno's latest gift, delivered in 2023 to 2024 with the extended mission gravity passes, is the measurement of tidal response. Jupiter's love number K22 is 0.5897 plus or minus 0.002, the most precise ever measured for a giant planet. That single number confirms that the density increases gradually toward the center, with no sharp discontinuities large enough to produce a visible tidal signature. The planet is as close to a perfect polytrope as nature allows, one single continuous fluid with no solid surface anywhere. 8 years, 61 close passes, and more than 400 terabytes of data later, Juno has replaced every cartoon of Jupiter's interior with a new reality, a world of liquid hydrogen 40,000 kilometers deep, capped by another 20,000 kilometers of normal liquid hydrogen wrapped in a 350 plus kilometer deep ammonia water weather layer, all sitting on top of a metallic hydrogen envelope that blends seamlessly into a half-dissolved primordial core. There are no clean lines, no neat boundaries, no compact rock ball. There is only gradient, flow, and pressure turning the most common element in the universe into forms that exist nowhere else. Juno did not just update our knowledge. It annihilated the old knowledge and built something stranger and far more magnificent in its place. We are now going to descend together into the largest ocean that has ever existed. An ocean with no shore, no bottom you can stand on, and no surface you can ever see from space. It begins only 1,000 kilometers beneath the colorful clouds we all recognize as Jupiter, and it stretches downward for 61,000 kilometers all the way to the fuzzy core. This is not an ocean of water. This is an ocean of hydrogen, the largest contiguous body of liquid in the solar system by a factor of thousands. At the cloud tops, pressure is 1 bar and temperature hovers around minus 108 degrees Celsius. As you fall, pressure doubles every approximately 60 kilometers because the density is so low at first. By 500 kilometers depth, pressure has reached 100 bar and temperature has climbed to plus 200 degrees Celsius. The hydrogen and helium mixture is still technically a gas, but it is already supercritical. There is no longer any meaningful difference between liquid and vapor. Molecules are packed so tightly that the old phase diagram we use on Earth simply stops making sense. At approximately 1,000 to 1,200 kilometers below the visible clouds, the exact depth varies with latitude and weather. Pressure crosses the critical threshold of approximately 12 to 15 bar for hydrogen at these temperatures, and the supercritical fluid finally becomes a true liquid. This is the moment Jupiter stops being a gas planet and becomes a liquid planet. There is no splash, no horizon, no wave. The transition is smooth, continuous, and invisible, but it is absolute. From this depth downward, 99.9% of Jupiter's volume is liquid. The upper layer, roughly 20,000 to 25,000 kilometers thick, is molecular liquid hydrogen, H2. It is transparent, colorless, and completely insulating. Electrons are still bound to their nuclei. Density here rises from approximately 0.1 at the top to approximately 0.5 grams per cubic centimeter at the bottom. Temperature climbs steadily from approximately 1,000 degrees Celsius at the top to approximately 9,000 to 10,000 degrees Celsius at the base of this zone. Pressure at the bottom of the molecular ocean reaches 800,000 to 1 million bar, 0.8 to 1 mbar, 800,000 times sea level pressure on Earth. To give you a feel for that number, the deepest part of the Mariana Trench is 1,100 bar. The core of the Earth reaches approximately 3.6 million bar. So the bottom of Jupiter's molecular hydrogen ocean is already experiencing pressures a quarter of the way toward Earth's core, yet it is still 40,000 kilometers away from the center. This ocean is deeper than the distance from Earth's surface to the orbit of geostationary satellites. If you dropped the entire Earth into it, our planet would sink like a pebble in the Pacific and vanish long before it ever noticed the bottom. The fluid is incompressible enough that density changes only gradually. That means the weight of the overlying column keeps crushing everything below with almost perfect efficiency. Every additional kilometre of depth adds roughly 30 to 40 bar of pressure relentlessly without pause for 40,000 kilometres. At approximately 40,000 to 45,000 kilometres depth, about 0.8 to 0.9 Jupiter radii, pressure crosses the magic threshold of 2 to 3 million bar and temperature is approximately 10,000 to 11,000 degrees Celsius. This is where laboratory physics completely breaks down and nature does something we have never seen anywhere else. Hydrogen undergoes a phase transition into metallic hydrogen, a quantum fluid in which electrons are no longer bound to individual protons, but move freely throughout the lattice like they do in copper wire. The transition is continuous. There is no sharp boundary, just a gradual increase in electrical conductivity that rises over a depth range of several thousand kilometers until it reaches values higher than any metal at room temperature. This metallic hydrogen layer is another 40,000 kilometers thick, extending all the way down to approximately 0.3 to 0.4 Jupiter radii. Density here climbs from approximately 0.7 to approximately 4 to 6 grams per cubic centimeter near the dilute core. Pressure at the bottom is 40 to 70 million bar. Temperature reaches 20,000 to 25,000 Kelvin, hotter than the surface of the Sun. The metallic ocean is the reason Jupiter has a magnetic field 20,000 times stronger than Earth's. Convection in this conducting fluid, driven by the planet's internal heat and rapid rotation, generates a dynamo that is not a thin shell but a thick, turbulent sphere occupying most of the planet's volume. Differential rotation, helical flows, and compositional buoyancy from helium rain and heavy element settling all feed the dynamo, creating the strongest sustained magnetic field around any planet. Inside this metallic sea, viscosity is extremely low. It flows almost like water despite the crushing pressure. Theoretical calculations and shockwave experiments suggest the viscosity is only approximately 10 to the minus 6 to 10 to the minus 5 meters squared per second, similar to liquid mercury at room temperature. That means storms and vortices in the metallic hydrogen can persist for millions of years, far longer than anything in the visible clouds. Heat flow through the ocean is enormous. Jupiter radiates 8.3 times 10 to the 17th watts from its interior, equivalent to a surface flux of approximately 7 to 8 watts per square meter averaged over the whole planet. Almost all of that heat moves upward through the liquid layers by convection. Giant cells and columns of rising and sinking hydrogen carry energy outward at speeds of meters to tens of meters per second. Those convective motions are what ultimately power the visible weather we see in the clouds, 40,000 kilometers above. There is no seabed. There is only deeper liquid, gradually thickening, gradually mixing with heavier elements that were once part of a compact core but are now smeared throughout the bottom half of the planet. This ocean has existed for 4.6 billion years and will continue for trillions more. It has no tides from outside. The sun is too far, no evaporation, no freezing, no day-night cycle. It is the most stable, most permanent body of liquid in the solar system. Everything we call the surface of Jupiter, the belts, the zones, the Great Red Spot, the lightning, the aurorae, everything is just weather in the top 0.1% of this ocean's depth. The real planet, the real Jupiter, is down here, in the dark, under pressure that would turn diamond into liquid and force electrons to abandon their atoms entirely. This is not a ball of gas with a liquid center. This is an ocean planet whose ocean is made of the lightest element in the universe, squeezed until it behaves like molten metal, and it is deeper than the width of 20 Earths, stacked end to end. 40,000 kilometers beneath the clouds, where sunlight has never existed and never will, lies a sea of liquid metal that behaves like no metal you have ever touched. This is the realm of metallic hydrogen. Hydrogen squeezed so violently that its electrons are torn free and drift through the fluid exactly the way they drift through copper or gold. The pressure required to do this is 3 to 4 million bar at the top of the layer and climbs to 40 to 70 million bar at the bottom. The temperature is 10,000 degrees Celsius at the roof and 20,000 to 25,000 degrees Celsius at the floor, hotter than the surface of the sun in the deepest parts. Yet it remains a fluid, not a plasma. It is the best electrical conductor in the solar system, better than silver at room temperature, better than anything we can make on Earth. This metallic ocean is 40,000 kilometers thick and occupies roughly 60 to 70% of Jupiter's entire volume. Its total mass is approximately 250 to 280 Earth masses of pure, freely conducting metallic hydrogen. For comparison, the entire mass of Earth's core, the only natural metallic conductor we have ever touched, is 0.32 Earth masses. Jupiter contains nearly 1,000 times more liquid metal in continuous motion than our planet has solid metal locked away forever. That ocean is the dynamo. It is the single greatest electrical generator orbiting the Sun. The mechanism is brutal in its simplicity. The planet rotates in 9 hours, 55 minutes, and 30 seconds. The metallic hydrogen is incompressible and highly conductive. Convection cells rise and fall at speeds of 1 to 10 meters per second, driven by the 8.3 times 10 to the 17th watts of internal heat. Helium rain, liquid helium droplets that condense out of the hydrogen-helium mixture around 1 to 2 megabars, adds compositional buoyancy. Heavy elements sinking from the dilute core add more. All of this motion stretches, twists, and shears magnetic field lines embedded in the fluid. Because the conductivity is essentially infinite on planetary timescales, any motion generates enormous electric currents. Those currents generate new magnetic field, which is then stretched again, creating a self-sustaining dynamo that converts a tiny fraction, roughly 0.01 to 0.1%, of Jupiter's heat flow into magnetic energy. The result is a magnetic moment of 19,519 Jupiter radius cubed times Gauss, or roughly 20,000 times Earth's magnetic moment. At the cloud tops, the field strength is 4.2 Gauss in the equatorial region and up to 14 Gauss near the poles. Earth's field is 0.3 to 0.6 Gauss. At the dynamo surface itself, the field reaches 20 to 40 Gauss in the strongest zones, and Juno's magnetometer measured localized spots as high as 60 to 80 Gauss during close passes. The field is not a clean dipole, it is monstrously lumpy. The northern hemisphere dominates with a concentrated flux bundle called the Great Blue Spot, an intense negative polarity region near the equator that is currently shrinking at 2 to 4 centimeters per second and drifting west. The southern hemisphere is weaker and more fragmented. This asymmetry is directly tied to the north-south gravity asymmetry Juno measured. More heavy elements in the north, stronger dynamo action, stronger field. The magnetosphere is the largest coherent structure in the solar system. On the sunward side, it stands off the solar wind at 3.5 to 7 million kilometers. On the night side, it stretches beyond Saturn's orbit, sometimes reaching 48 million kilometers. Total volume, approximately 2 times 10 to the 10th power times the volume of the Sun. No other planet even comes close. Inside that magnetosphere, the radiation environment is apocalyptic. Juno's radiation vault, a titanium box the size of a large suitcase with 1 centimeter thick walls, still received 20,000 to 30,000 rads per orbit. The flux of greater than 10 mega-electron-volt electrons reaches 10 to the 8th centimeters squared per second near the equator, and greater than 50 mega-electron-volt protons exceed 10 to the 5th centimeters squared per second. At Europa's orbit, the dose is 500 to 600 sieverts per day. An unshielded human would receive a lethal dose in under 10 minutes. The aurorae are the visible proof of the dynamo's power. Juno's UVS instrument measured auroral power input of 10 to 15 terawatts continuously, hundreds of times brighter than Earth's most intense displays, with occasional bursts exceeding 100 terawatts. The polar aurorae cover areas the size of Earth and glow in X-rays because 100 mega-electron-volt electrons slam into the atmosphere. The footprints of Io, Europa, and Ganymede are visible as bright spots trailing the moons, powered by millions of amperes flowing along magnetic field lines. The metallic hydrogen also explains why Jupiter's field has remained strong for 4.6 billion years. On Earth, the dynamo will eventually die when the core cools. On Jupiter, the heat source is gravitational contraction plus helium rain plus primordial heat, and it will keep the metallic ocean convecting for trillions of years. The field will still be there when the Sun swells into a red giant and swallows Mercury and Venus. Laboratory confirmation of metallic hydrogen finally arrived in 2021 to 2023 when two independent teams, one at the National Ignition Facility, one at the Z machine, briefly achieved the phase in diamond anvil cells and shock compression. Conductivity jumped by 6 orders of magnitude at 3 to 4 mbar, exactly as predicted for Jupiter. The phase is real. It is stable under Jovian conditions for billions of years. And it is the reason Jupiter owns the most powerful magnetic environment around any planet. Everything we see on Jupiter, aurorae, radiation belts, radio bursts, magnetospheric storms, is just the exhaust of this titanic liquid metal generator spinning in the dark. The clouds are irrelevant to it, the storms are irrelevant. They are weather in the insulating foam that floats on top of the real engine. The metallic hydrogen ocean is Jupiter's heart, its power plant, and its shield. It is the single most extreme macroscopic quantum fluid in the solar system, and it is alive, churning, and generating a magnetic field that would fry any spacecraft that dared to dive into it. This is not a planet with a magnetic field. This is a magnetic field with a planet attached. We have reached the final mystery, the place where even Juno's instruments fall silent, and only mathematics dares to speak, the center of Jupiter. There is no solid surface anywhere in the planet. There never was. Yet something is down there, something that contains between 15 and 30 Earth masses of rock, metal, and ice. The original seed that started the whole monster growing 4.6 billion years ago. We used to draw it as a neat, compact ball about 1.5 to 2 Earth radii across, surrounded by a clean boundary like Earth's core mantle interface. That picture is gone. Juno destroyed it with 8 years of gravity measurements so precise they can detect a shift of 1 centimeter per second in the spacecraft's velocity from 100,000 kilometers away. What replaced it is the strangest object in the planetary inventory, a fuzzy core, a dilute core, a core that is not a core at all. The heavy elements do not sit in a dense sphere. They are smeared outward over a region 80,000 to 100,000 kilometers in diameter, roughly half the planet's entire radius. The central density is only 6 to 12, not the 25 to 30 grams per cubic centimeter we expected for a pure rock iron ball. Instead of a sharp jump, the density rises gradually from approximately 4 in the deep metallic hydrogen to approximately 10 to 12 grams per cubic centimeter near the center, and then simply stops increasing. There is no boundary. There is only a thick, slushy, partially dissolved soup of silicates, iron compounds, water ice, and metallic hydrogen, all mixed together in a single convective layer that extends from approximately 0.4 Rj all the way to the center. This is the dilute core, and it is the direct scar of a titanic collision. Sometime in the first 10 to 20 million years after Jupiter formed, a rogue protoplanet, mass between 10 and 20 Earths, slammed into it at 20 to 40 kilometers per second. The impactor was not deflected or captured. It punched straight through the young envelope and detonated near the center, releasing energy equivalent to 10 to the 40th joules, more than the sun emits in an entire second. The shock vaporized the impactor, vaporized most of the original compact core, and drove a planet-scale mixing event that flung heavy elements outward in plumes that reached halfway to the cloud tops before falling back. The metallic hydrogen, still forming at the time, acted like an ultra-dense fluid that absorbed the debris and refused to let it settle again. Convective currents, powered by the fresh heat of the impact plus ongoing accretion, kept everything stirred for hundreds of millions of years. Even now, 4.5 billion years later, the heavy elements are still slowly trying to sink, but the dynamo flows are strong enough to keep them partially suspended. Computer simulations, the most advanced being the 2020 to 2024 SPH and grid codes run on NASA Pleiades and Frontier supercomputers, all agree on one thing. If the impact was head-on or nearly head-on, the core never reforms. The eroded material stays distributed. Only grazing impacts produce a compact core again, and those are statistically rare. Jupiter's observed gravity harmonics match the head-on collision scenario almost perfectly. The asymmetry between north and south is the leftover tilt from the impactor's trajectory. The fuzzy core is still evolving. Heavy elements are sinking at a rate of millimeters to centimeters per year, releasing gravitational potential energy that contributes roughly 20 to 30% of Jupiter's current internal heat flux. In another 5 to 10 billion years, they will finally coalesce into a proper compact core, but by then the Sun will be a white dwarf and Jupiter will be orbiting a cold corpse. This structure explains every major puzzle Juno found. The massive north-south gravity asymmetry. More heavy elements are still concentrated in the northern deep interior, exactly where the impact plume would have carried them. The huge odd harmonics. They are the fossil gravity signature of giant convection rolls that originated from the impact mixing. The high water and heavy element abundance. The impactor delivered 10 to 20 Earth oceans of water and silicates that were mixed throughout the envelope instead of being locked in a core. The thick dynamo region, metallic hydrogen extends deeper than in any other model because there is no insulating solid core to cut it off. Saturn, by contrast, shows much smaller gravity anomalies and is believed to have a more compact core, implying it either never suffered such a collision or the impact was glancing and less energetic. Uranus and Neptune have even smaller cores and completely different dynamics. Jupiter's fuzzy core may therefore be unique among known giant planets, a cosmic accident frozen in time. The final proof came in 2023 to 2024, when the Juno team combined the full gravity dataset with new equations of state for hydrogen-helium heavy element mixtures under 70 megabars and 25,000 kelvins, developed using Sandia Z machine and NIF laser data. Every single model that includes a sharp core boundary fails to match the observed tides and gravity coefficients by factors of 100 to 1000. Every model with a dilute, mixed central region fits within measurement error. So this is the center of Jupiter, not a ball of rock, not a solid anything, but a 100,000 kilometer wide region of dense metallic slush suspended in the slowest, heaviest convection current in the solar system. It is the ghost of a dead world that tried to kill Jupiter in its infancy and instead became its heart. Everything we have learned, the liquid oceans, the metallic dynamo, the wet envelope, the asymmetric field, flows from this single ancient catastrophe. Jupiter is not a planet that formed gently. It is a planet that survived its own attempted murder and turned the weapon into its defining feature. That is why it is still radiating twice the sunlight it receives. That is why its magnetic field is a monster. That is why its interior is one continuous gradient with no walls, no floors, no ceilings. Jupiter is the only world we know that ate another world so completely that the victim is no longer a separate thing. It is dissolved, distributed, and still sinking 1 centimeter per decade toward a center that will not fully exist for another 5 billion years. This is the final truth Juno has given us. The largest planet in the solar system has no center in the way we understand centers. It has only a memory, a dilute, dissolving memory of the day it was almost destroyed and instead became something greater.